Hello and welcome to today's Wolfram Institute live stream. Today we're joined with Ellynne Dec, who will give some really logical investigations and examples of from our art practice. A lot of cellular automata inspired beadwork. Look forward to seeing some of that. Ellynne, welcome and thanks for joining. And go ahead.
Okay, thanks. All right. So I have a bit of a script so that I don't go too crazy and off the terrain. So bear with me. I'm going to present a few pieces of Ruliology that were inspired by my art practice, and these are from 3 community posts that I've done. So you can check those out if you're interested. There are a few links scattered throughout this presentation for those. One of the posts that I will be referring to is about how we can use basic Boolean logic to build 108 of the elementary cellular automata rules. One of them is about error propagation and the differences between rules. And the third one, which I actually haven't posted yet, but I've written up, is about how rules behave on alternative grids. Anyway, I'll present some of those the insights that came from these 3 Ruliological explorations. And the first 2, I think, are pretty quick. And so we'll probably spend a little bit more time on the third one, which is kind of more complicated to explain. So I appreciate this chance to share it and try to learn how to explain it a bit better. First, I'll do a little bit of context. And at the end, then I'll talk more about my art practice and some of the ideas as to how it relates to other computational topics. And just to let you know in advance, I've timed this to 30 minutes, but I'm very happy to be stopped along the way for comments or questions, however people are comfortable. And also, I've assumed a certain level of proficiency with cellular automata and a new kind of science. And I go straight for some fairly technical terms at times, but let me know if you think I should stop and explain more. I don't think it's going to be an issue for this audience, but don't be shy if I'm too speedy. All right. So, my slumpy forms. My fascination with simple computational rules really began when I was very young. But at the end of 2024, I was completing a series of artworks investigating growth and simple forms. In this work, I was creating sculptures by weaving beads into tubes, propping them up, and examining how they slumped and sagged and found their own equilibrium. I was engaged in these topological and tactile investigations, studying morphology and Renee Tom's catastrophe theory, and I was geeking out over deep notions of folding and contortion and projections in space. So that was kind of my art practice at the time. I was looking at Annie Alber's work and wondering about the evolution of pattern, and I started to wonder if weavers and mosaicists and stoneworkers, etc., were actually using the same basic rules to create their patterns. And like any good computational nerd, I happened to already have a copy of A New Kind of Science on my shelf, so that's where I turned. And while my first investigations were with graph paper and pencil, I wanted to experiment with cellular automata in rules in my beadwork. And since I was doing beadwork in the round, I wondered about translating the rules that I was reading about from a flat and potentially infinite plane, the way that they're described in New Kind of Science at the beginning, especially, to a tubular grid topology, like the ones in my slumpy forms. Now, I hadn't used Mathematica since like 1995, but I was open to relearning. And so I posted on the Wolfram Institute Discord to see if I could get some guidance out on how to model these ideas. It was very brave. And Nick and Dugan replied, and somebody was kind enough to drop in some code, and that was actually a year ago yesterday. So it's kind of very poetic to be presenting to you all today. All right. So I should also say, when I was planning to weave in these patterns, I was not interested in looking at a paper pattern or even a set of rules. I wanted to be weaving. I had to fully internalize the rules that I was using. So if I was going to use these rules for bead weaving, I needed to identify a rule with an interesting pattern that was easy to memorize. And I have a terrible memory, so this was kind of a high bar. All right. So we come to Rule 90. Somehow, I don't know how, I managed to hone in pretty quickly on Rule 90. I mean, it's a visually interesting pattern. It's Sierpinski-like, kind of classic pattern, and it turns out to be surprisingly easy to learn. And this is because, as many of you know, Rule 90 is just XOR on the left and right neighborhood cells. So, you can kind of see that. I don't know if you can see my pointer,
We
but
can see
if
your mouse.
you okay. So, if you're looking at this situation, XOR tells you that if you look at the left and right, they're both ones. And so XOR tells you that this would be a zero. And here you're looking at the left and the right, and left is a one and right is a zero, so you get a one. And that continues on. So rule 90 is just XOR on left and right. And that's quite beautiful. It's incredibly simple. Obviously, it's very easy to memorize. So I hit the ground running. All right. So the first ruleology I want to discuss is this. I realize that Rule 90 is XOR, but also, of course, Rule 60 and 102 are XOR, just on different two cells. So Rule 60 is XOR what on the left and the center, and Rule 102 is XOR on the center and the right. Um, and so I wondered, what if I forgot and I was beating and I forgot which two cells to look at? What would be the result? How robust is this XOR to sort of mistakenly looking at the wrong two reference cells as I'm going through a work? So let's see. Why is this not to go to the next cell? All right. So my first piece of ruleology that I really did in Wolfram language, aside from the basic kind of looking at patterns, was coming up with a way to look at a random sample of Rule 60, 90, and 102 if I were to be a little bit forgetful and chaotic in my approach. And it turns out that it actually doesn't matter much. As long as you use mostly the same two reference on any row, you'll get a shape that looks roughly like what we expect. It's XOR-like, it's Sierpinski-like. And so it turns out, so I realized XOR is actually a really robust rule for pattern generation, which for human makers is incredibly handy. In fact, it's the situation that you don't even, if you left one day, if you were making a rug using XOR and you left one day and your team, another person came to pick up the same rug the next day, they wouldn't even need to know necessarily if you were using the left and the right, although they could probably guess that. They could just start and use whatever their preference is, and you're going to get a pattern that's roughly behaving the way that you want it to. It might not be symmetric, but it's going to look like the rough pattern. So
That's
this
really
is very
interesting.
handy.
So,
Yeah.
if I'm understanding this correctly, like each row is using a random choice of rule 90, 60, or
Yeah.
102 to say like,
Yeah.
uh, look at the left and right and the window and do an XOR on that, or look at these two or these two, and
Yeah.
yeah. So invariably, like you get the triangles are always there. Sometimes they're more dense. Like I see that like little clustering. Um, that's a lot of fun. That's really cool.
Yeah, yeah. So for human makers, that's incredibly convenient, right, in art and design. But also so to me, this suggests that it's very convenient for nature too. So for systems that evolve using XOR type rules, it's a very forgiving and adaptive kind of rule set to use. So that made me think, how many other rules are made from basic Boolean logic relationships? And how many other rules could be this easy to learn and remember for human maker? I was quite surprised by this. So the simplest way to think about this was to use the basic Boolean logic operators that take two values as inputs and kind of systematic, and that's or, and I'll just add in XOR because I like it so much. And then uh, pair them with three different ways we can make pairs of neighborhood cells, right? So left and right, left and center, and right and center, and figure out how many different rules we can make using this general framework. Now, obviously, there are more clever things that we can do to expand the number of rules that we can access with this approach. And so the next thing that I'll talk through is how come, oh no, sorry. Right. No, sorry. Yeah. All right, so now I'll talk about how we can get to 108 rules for human makers. I think there are even more rules for human makers that would be easy to memorize, but these 108 are the ones that I develop systematically. So, um, so basically, the more general formulation that I use, I think of all three cells in the neighborhood tuple as playing different roles. One of the position one of the positions could indicate which logic relationship to use. And I'll give you some examples to explain this later, or to sort of illustrate it a bit better in a moment. So one of the positions indicates which logic relationship to use, and I call that a check position. And depending on the value of the check position cell, the associated logic relationship would then be applied to the values in two of the neighborhood positions. So for example, Rule 110 uses the left cell as the check position. If it's a 0, we use OR on the center and right cells. If it's a 1, we use XOR on the center and right cells. So it's a relatively simple thing to then memorize. You don't need to memorize all 8 states. All you have to know is that if I look at the left cell, I'm in OR land. If it's a 0, if I look at the left cell and it's a 1, I'm in XOR land.
I like that. So
And
there's a
then
function which reducibly computes that specific rule.
exactly. Rule 30 uses the leftmost cell, also uses the leftmost cell as its check position and returns OR if the leftmost cell is a 0, so just like Rule 110, but it returns not OR if the leftmost cell is a 1. And again, the reference cells in this case are the center and the right. So I'm using all 3 of the neighborhood cells. One is a check position, the other 2 are the reference. But the check position could also be a referent, which is how you get to 108 rules. So Rule 30 also can be expressed in a very elegant way. It's the opposite of the left cell unless center and right are both 0. So that's also kind of really, it makes it even easier for a human user to memorize. And in fact, I mean, if you're ever in a bar and you want to bet somebody that you can do Rule 30 faster and with better accuracy, all you need to know is this statement and you'll be able to compete with the best.
I like that.
Yeah. Rule 54 is like Rule 30, but with the center cell as the check position. I mean, using this approach, you can see relationships between rules that are not quite as obvious when you're just looking at the Boolean representation. So Rule 54 is OR on left and right if the center is 0, and it's not OR on left and right if the center cell is a 1. And so just as a reminder of what 54 looks like, it looks very different from Rule 30. Looks more like kind of a much more regular checkerboard thing. So I find this quite interesting.
That is interesting. It's a permutation on the same logic, right? You're using like the left the center instead of the left as a check, and using the same like or and nor on the other two. But because of the positioning, you get like one pattern that has, it's Rule 30. Maybe you could show that as a for our art, for the video stream. But this one's very regular, very computationally reduced. Rule 30 is chaotic.
Yeah, Rule 30. Oh, sorry. Yeah. I think you could probably, let me just do this and see if I can throw it in here. It'll probably make the whole thing blow up, but uh-oh.
No, just
Yeah, it's gonna probably, yeah. I just
no.
have to,
I think it'll
well,
be all right.
I have examples of Rule 30 later, so
Okay.
we'll be able to see. All right, sorry. So let's see, I'll go to the next slide. Right. So here I tried to catalog the relative contributions of each of the additional Boolean logic gates to the total possibility space of elementary cellular automata that could be created using this method that I kind of developed, and that's in one of my community posts. I won't spend time going through this. There's like accounting details, but essentially it's we get 108 possible rules. And what I think is interesting is that in theory, all of these rules should be fairly easy for a human maker to memorize and describe in language and teach to other makers. Um, and uh, and so this is I think surprising. It's all more than half of the rules, in my view, should be very easy to compress into language, and some of them in ways that's even more efficient than in some sense the way that they're represented in the canonical form in New Kind of Science. All right. So that was the sort of main results of the first community post um, that I shared on Wolfram Community site. All right. Then the next thing that I just wanted to quickly touch on is around rule differences and error propagation. So as I started beating using Rule 90, and as a human, I make mistakes along the way. Um, Now, there's a whole conversation to have about error and mistake, which is very interesting. I touch on that sort of toward the end, but I want to be thinking about that more in the year to come. But for now, I just want to focus on how XOR also turns out to be a great way for talking about damage and repair, and for when we want to examine the difference between two Boolean matrices of the same size. So to highlight differences, we just have to use XOR on each matching element from between two matrices, and that will tell us where there's a difference. Um, so using this trick, I cataloged the single changes on 250, all 256 elementary cellular automata. Um, and I know this is something that's been done before, so I won't spend time on this here, but I do want to highlight a special case of differences between two rules. Among the 108 rules that we can generate using any basic logic function, I began studying Rule 105 and Rule 150, which are similar rules with particularly elegant heuristics. You can pick any of the three cells to use as a check position, and then just apply XOR to the other two cells. And the check position just sort of tells you whether to knot the result or not. And so this is quite cool. You can go through the logic on your own, but what I want to show you here is just that the result of 150, how the result of 150 compares to 105. So you see 150 here and 105 here, and it turns out that the rule differences when you subtract them, no matter whether you start from this sort of canonical um, single black cell type formation, or if you use random initial conditions, you get just a stripe, just stripes. That's the difference between 105 and 150. And again, it might not be obvious, although when you see these, the rule plots are kind of inverses of each other. So that might suggest that that's what happens. But in other rule systems where the rule plots are inverses of each other, you don't necessarily get stripes, right? So this is a special relationship between 105 and 150. And I think it's because, and one can kind of try and hone the understanding, the intuition as to why that is by looking at this expression of the rules. Use the opposite of the center if left equals right is rule 105, and use the same as the center if left equals right is rule 150.
Uh-huh. Right. So this red thing, this XOR difference, basically you're taking the output of one and the output of the other, and as if the pixel is like over here black and it's over here white, then the XOR of 1 and 0 is going to be 1. And so that's going to come up as a red pixel.
Yeah.
Okay. So
Yeah.
then, yeah, I can see that happening. When the center cell is different or the same, you'll have when it's
It's gonna be
different,
gray.
you'll have
When it's the
a
same as gray
red output. When it's the same, you'll have a white output in in the XOR.
or gray here in
Yeah,
this,
yeah. So
but
that's red and gray, right?
yeah, yeah,
Oh, that's very
yeah.
interesting.
Yeah, so it's pretty interesting, and there's I have some manipulates and various crazy things in my community posts that if people are interested in this, you can kind of dive in. But to me, what's important and interesting about this work is more that it's sort of helping me to get more of an intuition around how these heuristic statements of rules kind of relate to each other. So this rule 105 and run 150, where 105 is the opposite of the center if left equals right, and rule 150 is the same as the center if left equals right. Those are very easy rules for human makers to implement. And also, again, I just sort of have to imagine that systems in nature would also find that like kind of very easy to do. Um, and so I'm very attracted to trying to like understand the implications of these types of rules. All right. Um, let's see. So now I haven't posted this paper yet, um, but it was inspired by the summer school paper that Chase Marangu presented in a Wolfram Institute thing back in September. So yeah. So first, I want to say a little bit more detail about my bead weaving process. I weave beads one by one in a loomless way. First, the needle and thread will go through the bead here labeled L. Then with the needle, I pick up a bead with the correct color, whatever the correct color should be, and that's bead S here in the illustration. And then I sew back through the bead, or sew through the bead labeled R. So that's kind of that's the fundamental mechanism of this bead weaving process. And then I move to the next little nook and have to do the calculation again. And then next nook, obviously the R bead becomes the new L bead. And then there's a new C bead and a new R bead. So that's how it works. And this is called peyote stitch. The beads labeled, if it's not obvious, the beads labeled L, C, and R are the neighborhood that I use to determine which color is added as beads S. Um, and uh, and I don't know, even though it's sort of shaped in a different way, it might not be obvious that this is actually different from the standard kind of Moore neighborhood, the rectilinear regular grid. Um, and this winds up making a really big difference. Peyote stitches on a brick grid, and this kind of maps to something they would call a hex grid. And it turns out that many cellular automata rules that appear chaotic on a regular rectilinear grid become much simpler when applied to a brick or hex grid. Um, None of them become more complicated, let's say that. They all become either simpler or pretty much the same. And I'm going to discuss what I think are novel ways to map a brick grid onto a standard grid. And so the idea is this. Instead of using sort of trig or geometric offsets, which is those are the methods I've seen before, and frankly, they just kind of are not it's particularly inspiring to me. I instead map the hex points onto a checkerboard version of the regular grid where I leave holes in space. And this allows me to mimic the hex arrangements relative to each other. So I'll just sort of scroll down and show this. So essentially how it works is in this 3 by 3 grid in the center here, there are 4 active cells that form the checkerboard. That's these 3 red cells. Those are the neighborhood. And then this white cell with an X, which is the cell that in theory I'm trying to figure out it's equivalent to the S up there. So this would be equivalent to the L, the C, the R, and the S. And in some sense, one can implement this computationally in a pretty straightforward way and leave these holes in the grid with just a different matrix representation, for example. You could represent those with threes or with not. It doesn't really matter. The key thing is that we're only really paying attention to every other cell in the grid. So it's a checkerboard substrate.
Right. And then in
Um,
the neighborhood, so if I may draw on this, because
yep.
it's hard to think about sometimes. So I guess the neighborhood of this guy is this one, and this one up top. And then downstream would be and this one, and
Yeah,
then this one
that's right.
as
Yep.
things that it's influencing downstream. Yeah.
Yeah.
So that's a hexagon essentially. Okay.
Yeah. Thanks. Yeah.
Absolutely. Yeah.
Right. So yeah, so that was one way of thinking about it. But then I realized, oh, and I should also say that was inspired by something that Brian Silverman said in terms when we were looking at Chase's presentation. He sort of was saying it's almost like going back in time. And that got me to think, yeah, exactly. So you could almost even think, well, why have these holes in space at all? Why not just set up a system where rather than when, you know, how when we're developing our cellular automata sort of plots over time, we reference back to the previous time layer in space. And that's the neighborhood for the next row. Why not reference back two time steps for the center cell, but just one time step for the left and the right? And so you don't even need to have holes in space. You can just progressively move through time, but your center cell, or, you know, even more general model could be any of these cells, could be n steps back in time, and other cells could be, you know, just one step back in time, or, you know, so anyway, the space and time that you're referencing doesn't have to be just that previous um, the previous step in time, right?
Hmm.
Which is like any recursive system. We know that it can always go back. We can always refer back further as well. Um, so this approach is just like the other one, but it sort of has no holes in space. We're evaluating, again, this is the S, we're evaluating it relative to those dark red cells, but here I'm acknowledging that the pink ones would have been evaluated in the time step before. So everything gets filled in. And it turns out that these are, so first of all, it turns out this is a lot like weaving. It winds up intuitively winding up being like weaving, which I think is really interesting because I'm actually weaving these beads, and weaving even in weaving textiles, you're sort of moving up and down and over and under the warp threads. And so this weaving is almost like somehow you're moving through a different dimension. You're sort of taking advantage of an extra dimension of freedom of degree of freedom to be able to navigate from one plane, the front plane to the back plane, and again. So I think this is quite interesting analogy. And that these two approaches computationally turn out to be equivalent, at least as insofar as you can see them in the plots. And so what this suggests to me, how I kind of described it to myself, is that when we look at information matters as much as where we look. So I just want to show a few examples of how this type of approach, this weaving approach, the hex grid, dramatically simplifies the visual representation of some of these rules. So Rule 30, which is our famous like chaotic rule, which the standard rule plot is for 30 is here to the left. Rule 30 becomes stripes on a temporal, and these are both the same. The temporal is the temporal offset, and the alternating is just where I left holes in the plot. Um, Rule 30 becomes stripes. And I think it's if one uses this statement that Rule 30 is the opposite of L unless C and R are both 0, you can kind of start to develop an intuition as to why it looks like stripes in a hex grid. Because C and R are basically aligned at an angle.
Oh, I see. Uh-huh.
And so that alignment, that angle alignment actually then winds up kind of organizing um, the the rule in a different way than when they're not aligned. They're sort of separated from the left cell.
Yeah. Cool.
Um, and a lot of this on a hex grid, unfortunately for a maker like me, a lot of the rules just become very uninteresting. They just become like big, just kind of completely squares of black or stripes like Rule 30. But fortunately, Rule 90 is one of the few rules that doesn't change at all. It's the same on a hex grid as it is on the regular rectilinear grid.
And that's because, well, is it the looking at the left and right, exploring
Yeah,
those two? Yeah, because those are
yeah,
still
yeah,
like on the same linear horizontal segment.
right. Yeah, yeah. So there are a lot of interesting, I have not gotten very far in really exploring the full implications of these kind of temporal relationships. But in the next slide, unfortunately, I'm not sure that I'm like as um, comfortable with using with live coding or using Wolfram language in a streaming situation. Oh, see, I did again. Um, oh, these are the hex grids on, well, I'll go back to the slide that I was, ah, sorry, I have to pretty much scroll through this quickly. Okay. Um, yeah, so there are a lot of grids that are kind of interesting to see. But if we have time at the end, I can try and pull them up. I'll just keep going for now and then come back to the actual, illustrations later. So Rule 110 is very interesting on hex grid in some sense. Aesthetically, it's kind of boring, but it's interesting because it just becomes kind of like a checkerboard. And when I realized that Rule 110 becomes like a checkerboard, I thought that, well, couldn't we just kind of almost imagine a system where one rule, say Rule 122, which creates a checkerboard pattern, is deployed to create a substrate, and then another rule, like Rule 30, um, winds up kind of being plays out on top of that substrate that was created by another rule. Or even a rule like Rule 110 might play out on Rule 122 or and then play out again on that substrate that was left behind sort of recursively and kind of almost digest itself that way. So to me, this idea of the substrate upon which the rule might be playing out could be itself determined by another rule or the same rule. Um, so this concept is one that I'm going to kind of continue to play with. But I think this is this kind of idea of nesting these rules as substrates to other rules is very interesting.
Yeah, that's interesting. Sort of have the neighborhood be determined by a different rule,
Yeah,
and then
yeah,
iterate on that. There's a
exactly.
lot to explore there.
Okay. So those were the sort of key Ruliological insights that I wanted to share, but I just thought I'd spend a little bit of time talking more about heuristics. Because I say this word a lot, and what I mean by heuristics is really a kind of English language description of a rule that kind of encompasses, that sort of concisely describes the rule without referencing necessarily the sort of eight canonical rule plot type of representation of the rule. Um, and this is a potentially pretty rich topic. I think it has a lot of applications to AI and types of machine learning things that I'm seeing in the literature, to the extent that I'm kind of able to follow along with some of these conversations. Um, so Rule 90 obviously is XOR, but in the material world, there's no real truth table to negotiate, right? When I'm working with beads, I'm not like thinking, is it true or false? And is this, I'm not applying XOR really. So we're just talking about beads here. So how does XOR, how does a truth table even apply? Well, in the beading world, I'm only working with two colors in a particular section. And I use one bead color every time left and right are the same, and another bead color every time left and right are different. It's as simple as that. I just use, say, red every time the left and right are the same, and green every time left and right are different. And I go on like that.
Yeah, I like how
Um,
XOR comes down to that. It's like you have two values. Are they the same or different? You're not checking like, is it either of them true or strictly either. Um, yeah, so it's XOR means what? That they're different.
that
That's all you're
that
checking
they're
if they're different.
well, yeah, and in some sense, it doesn't even. Yeah, it's just, is it the same or is it different? XOR is just asking, are these the same or are they different?
Mm-hmm.
Which is very different from and or, where in some sense with and or, you kind of have to have some baseline reference as to which one is returned, um, which one has a sort of dominant role.
Yeah, which one is
Uh,
true, which one is false? As like if it's green or purple, like you got to remember. Okay, well I'm using purple as the value for true, kind of
Yeah.
thing.
Yeah. It actually turns out not to be the case, that you actually can get away with never mapping to you
Yeah,
don't
yeah.
have to actually map them, right? But
XOR is
it's
agnostic
counterintuitive.
to which orientation you have the values set. But
Yeah.
and
Yeah.
is not, and you have to remember, okay, well, like green and purple, or purple and purple is green if I'm using green as the the value for true, and purple as the value for
Right.
false, kind of thing.
Right. Although with XOR, you still have to think like, okay, this is like, I'll use red if it's the same.
Mm-hmm.
And so you do have to there is something you have to hold in memory, and that is which color is the color that you're going to use if it's the same. Or you have to hold into memory, this color is the color that I use if they're different, but you have to hold one of those things into memory. But that's it.
Mm-hmm.
Then otherwise you can kind of take, yeah, yeah. So it's quite different. It's quite interesting what the minimal information state you need to have in order to deploy some of these rules is very, very you need very little information. Um, so let's see. Um, yeah. And it turns out that the most important thing is to be consistent. So, like we were just saying, it doesn't really matter what color maps to true or false. It just is important to be consistent. And so, in other words, true and false, they're just labels. And I mean, that's obvious to say, right? But I think we operate in life thinking that there's something special about true and false, but they're actually just labels. And in the materiality of the bead world, truth tables are just a convenience we use for consistency. So consistency is the important thing, and the truth tables are a way to maintain consistency. So it's not like anything is special about true and false. It's just we want to be consistent. Um, and yeah, so Rule 90 just cares about same and different. And it's actually kind of the same. The story is somewhat similar with and or, but I think with X or it's just much more powerful and even simpler. So here's Rule 90 and just some illustrations. This is the rule plot for Rule 90, which we all know. And if we, obviously, you know, Wolfram language is basically telling us, it's giving us a beautiful way to just say, and it doesn't even matter if it's true or false, 0 or 1, black or white. We could just say like, okay, and by the way, 0 is red and 1 is green, or 0 is green and 1 is red. It doesn't even matter. And so these are some plots where I just kind of said, I kind of identified sort of in a sort of more bead world, I might have a whole bunch of different kinds of green and a whole bunch of different kinds of red. And all I have to do is keep the reds and the greens separate and be consistent about how what I'm doing when things are the same versus when they're different. Um, and so this is all, I think, quite deep, kind of like simple, beautiful stuff. All right, Rule 30. And Rule 30, again, I mean, for such a complicated rule, it's actually really, the heuristic is really nice. So in a two quality world, so when I say two qualities, I mean like two colors, or with beads, some beads are shiny and some are matte. So sometimes in my bead weaving, I'll play around rather than saying red or green. I'll be like, okay, I'll put a shiny bead if they're the same, and I'll put a matte bead if they're different. Or I'll put a clear bead if they're the same and an opaque bead if they're different, or whatever, right? It kind of, what's cool is there are a lot of ways you can play around with this, but you get, the consistency is what matters, and you have these emergent patterns that have so much complexity, but they maintain a kind of overall consistency. So this is very, very powerful. So Rule 30, which is very easy to do once you learn the opposite of left, unless center and right are both, I'll call here background colors. So here, in this illustration on the left, the background color is green. So the way that I would deploy Rule 30 if I was doing it by hand is just say, okay, is the left green, or is the center and left both green? Yes. Okay, then let me use the same as what's in the left. Are the center and right both, not both green? Okay, then I use the opposite of what's in the left. And you just kind of can quickly move, manually across. So here it just says, I've just tried to show, again, like in the Rule 110, or in the Rule 90 from the previous slide, if they're both the red and green versus dark and light. So if I had a whole bunch of beads that are both red and green, but some were dark and some were light, I could differentiate them that way. So here the background is a dark color. So the checking is against whether both C and R are dark. And that tells me whether I use the opposite of left or not. And here the background is light. So it's very interesting to see how simple and flexible these rules wind up being with these heuristics. Rule 86 is the opposite chirality of Rule 30. So rather than looking at the left cell, you look at the right cell. So you use the opposite of the right cell unless the center and the left are background. And Rule 225 is kind of interesting because it says to use the same as the left cell unless the center and right are both backgrounds. So it's very similar to Rule 30, but you get such a different result.
So it's very similar logically then,
Yeah,
but the outputted pattern is quite different.
yeah.
Oh, that's
This
interesting.
is, yeah, it's kind of crazy. Yeah, it's very interesting. It's because the formulation is so similar. Rather than the opposite of left, it's the same as left, unless C and R are both background. And
Hmm.
I don't know what rule it is, but you've got, I mean, for sure, there's a rule that says to use the same as R unless C and L are both backgrounds. So, and I'm sure it looks like this, except that the green thing goes in the opposite way.
Hmm.
Yeah. So this opens up a lot of different ways to catalog rules and to develop what I want to do is to develop a library of heuristic descriptions of rules so that in our we have a way to always know what a heuristic representation of any rule is. Um, and I think that almost all of them can be described in words. And we can do it quite systematically. It's not just sitting and meditating on the rules and figuring them out. The 108 um, logic rule structure gives us the starting point to develop these even more concise expressions that work in many cases. Let's
Right,
see.
right. And it was interesting to note that like the remaining of the 256 cellular automata in this way don't have a simpler logic underpinning to them. This is
Well,
just like
some
arbitrary.
might. So there, yeah, some
Mhm.
might. So you can kind of imagine like rules that I didn't include in the 108 where if the left cell is a 1, use the opposite of the right cell. If the left cell is a 0, use and on the center and right. So what I didn't do is sort of um, set up that computation to also include the cases where you're applying just, like a not or a same as. So there
Mhm.
are actually even more that potentially could be described. So I think actually very few of the 256 would be excluded from this space of possible kind of heuristic descriptions. I think that many more rules can be described in plain English than can't be. Um, and we could probably put out a bounty on the ones that we think can't be. That would be sort of fun. Yeah. Um, all right. So let's see. Yeah. Um, Oh, yeah. Another thing that I realize is that so when I'm weaving, I sort of like to think of myself as a computer, like a little bit sad. And so I invite you to sort of imagine you're in a little nook. You're like a little bead, and you look to your left, you look to your right, you look straight ahead. And I mean, we were talking about this before. Instead of white or black or 0 or 1, any substitution system will do. So I was talking about the color or the sort of quality, whether it's opaque or clear or shiny or matte. But actually, another thing that I wind up doing is I tell myself these stories as a work will evolve. And I sort of think of one bead quality as sort of native and the other bead quality potentially as invasive. Or one bead is foreground and one is background, or one is positive and one is negative, or open and closed brackets, which is another mechanism that Stephen Wolfram uses in New Kind of Science to kind of describe how some of these I think it's combinators kind of can be expressed as cellular automata. He puts a different color on the open versus the closed brackets. And this is a very interesting kind of general sense. But what I find interesting is there always seems to be some sort of a valence. There always seems to be some sort of a hierarchy in these relationships. So another thing that I noticed that when there are only two possible choices, like red and green, The heuristics can be silent on the default case. So, where I say, always use the opposite of this unless, um, you know, center and right are the same. What it means is that then you would use the same as left in the other cases, right? But I don't say that explicitly in the heuristic. It's just
Mm.
implied because there are only two possible rules, and one has to understand at some level that if the rule is not explicitly stating what to do, then you should be doing some other thing, and that other thing needs to be kind of understood as a default state. And that holding that default state is something that the system has to also be able to do. The system has to know what the default state is, and then also the rule for the exception state. Um, but as I add more colors or qualities to the mix, I have to modify the rules somewhat based on the new relationships that are created by these new colors that enter into the mix. And so this how that works is super interesting, and I'll talk about it a little bit more in the next slide. Um, I think not quite sure why I put these rules here, but just more examples of foreground and background. Rule 122 is a checkerboard rule. And so Rule 122 was basically how I created those checkerboard substrates in the previous Ruliology that I talked about, to mimic the hex grids. And so I used Rule 122 to generate the substrate, and then I applied all the rules on top of the cells that would be ones in rule that were turned up as ones in Rule 122. But 122 is very cool. I just want to like celebrate Rule 122 for a moment, because on a regular on the canonical form, it's a checkerboard, but the minute you introduce any kind of randomness, it goes kind of, it turns into a more chaotic triangular set of triangles that is
That's really
difficult to.
interesting. So with like a purely black background and a single white square as the initial condition, it makes a checkerboard. But with a random string, a random initial condition, it'll have a randomized output.
Yeah, what I did here is I messed with the foreground and the background. So I
I see.
actually changed. So 122 actually canonically would be white background, black cells. I
Hmm.
messed with it here just to kind of make the point that really it doesn't matter. And we pretend
Yeah.
that there are
Yeah.
256 rules, but actually there's 128.
Right. Right.
Um, and I think that that's, I don't know. I feel like yeah.
Yeah.
But Rule
Up to color
122,
symmetry there. Yeah.
right. So Rule 122 is very cool. All right. Let's see. So here we are. All right. We got through that. Um, all right. So I just want to say a few words about working with beads. Working with beads, I'm drawn to metaphors of particles, of bits and atoms, of cellular growth and form as information storage. I play around with specific aesthetic considerations around grids and pixels and transitions and symmetry. My artwork could be digital, but somehow I remain stubbornly material. Of course, there is an absolutely ancient cultural role of beads as counters and tokens and records of information, and I don't think these roles are an accident. The torus is the perfect form for these roles. The hole in beads enables them to stand in relationship between the physical and the abstract, the tangible and the digital. In ancient practices, I can imagine that many of these rules were communicated without words, with samples or stones or other tokens. But even in primitive weaving done in groups of workers who may have worked in tandem or in shifts with poor lighting conditions or in bright sunlight, we see complex but coherent patterns, and I suspect that they were achieved with the consistent application of very simple rule heuristics. All of this suggests that basic computational rules and consistency unify all pattern makers from the beginning of time. This is also, of course, a computational investigation. I try to behave as a computer, running an algorithm referring to indexed cells in a relative neighborhood. And I wonder, what would the system be like if it were actually autonomous? What minimal code would have to run on the tip of the needle? What sensors would be required? When I introduce new colors, the system becomes more complex. New demands are made upon the components of the system to negotiate the right rules. Depending on the rule at work, there's also a logic to how the rules evolve. Dynamics such as hierarchies must emerge to maintain coherence. I plan to do more work to articulate these dynamics. I'm also fascinated by how valuable symmetry is to a human maker and to nature. It's a free lunch. Rule 90 is symmetry preserving, as are many of the elementary rules. Monitoring for errors, especially at early stages, is achieved with visual cross-reference. In fact, there are many mechanisms in nature that one can imagine can be co-opted to monitor for symmetry as a proxy for error. Okay, finally, to sum up, I want to promote a conversation about art for robots. This is not simply about computational aesthetics. I'm also interested in how art objects might help unlock a kind of intrinsic motivation for discovery among artificial intelligences. To ask this in a more concrete way, how can art objects create interactive training data for aesthetic sensing? How art might enhance understanding between synthetic and human intelligences, and how artworks such as these beaded tapestries, showing the complexity of simple rules that speak to the algorithms behind LLMs and our computational universe, how can they remind humans and robots of the poignant beauty and the computational limitations we all face? So that was my little poetic bit on my,
Well said.
and I just want to thank, of course, Dugan and Brian for encouraging me with this work as it's been evolving over the past year. Ahmed's been super patient with my kind of unhinged postings in the community, and I so appreciate that. And then at summer school, Jambor, Phileas, and Bowen were incredibly helpful mentors, and also beyond summer school. And of course, thank you to Stephen Wolfram for seeing the relevance of this very quirky approach to Ruliology. Um, it's really changed how I think of my art practice, and it's become art and Ruliology all at once. So, and then anybody who's seeing this who doesn't already follow me on Instagram, follow me, please, because I post a lot of beautiful pictures of my beautiful work. It is beautiful. You
Yeah, I
can look at
posted
it
a link
again.
in the video description on YouTube. Um, Link down below in the doobly doo. Yeah, I was gonna
Yeah.
say, please go back to this picture. A lot of questions here. So it seems like on the left and the right, the initial condition along the outer edge are the same, and you're using the same rule throughout, correct? Uh, XOR
Yeah.
on the
Yeah. It's
on the left and right.
yeah. So basically I start at the center,
Oh,
and I start with just three beads.
mm-hmm.
It's sort of embryological in a lot of ways, sort of more, how I'm very interested in how it grows. So I kind of do three beads of the same background color for a few rows. And then I introduce some new colors.
Uh-huh.
So that's where you get so it's always the same, the same, the same. And then suddenly I introduce a few difference. And I introduce difference in a symmetric way by design, but I note that in nature, we one would be kind of probably working in more of like two cells split and cells split until they're splitting in different ways, and that kind of also creates a kind of symmetry. Yeah, and so yeah, you can see that Rule 90 is at work already. You can almost split it into three panels. This top panel is have this sort of biax is this biaxial symmetry? Um,
Yeah.
And the top third is symmetric across, right? And then these two sides are roughly symmetric with respect to each other. And so
That's
yeah, I
interesting.
just rule.
I didn't see that as being nucleated from the center growing outward. I always thought there was like you took this segment and cut it into a triangle and then stitch those triangles together. But you made this whole thing from the center outward. That's cool. That's really cool. So you get something which is very unique. Um,
Yeah, it's like planting a garden in some ways.
hmm
Like you don't know. So up until this point, I don't know if you can see this triangle. The only colors that I have in there are the sort of dark green and that silvery color. Here you see a sort of different kind of gray. I think I introduced a new quality in there. Um, so because I have experience with how the Rule 90 pattern evolves, I've sort of developed an intuition for knowing when I'm able to introduce the when we're about to launch a triangle, when a triangle is about to emerge. So in a place where I know a triangle is about to emerge, I can introduce a design choice. I can say as a human maker, well, this triangle, I'm going to make a slightly different type of gray
hmm
than the rest of the ones, right?
So you're
So
changing
I
like
just
the
choose,
background color or the foreground color.
yeah, this is a foreground color.
Uh-huh.
Uh, yeah, yeah. Oh no, this is a background color. You're right. Yeah. Yeah. So
I wasn't sure, so
there's a
I
funny thing that
used both
happens.
words.
Yeah, 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 yeah. It's actually, it also shows you that it almost like the role is always very local. It's all the rules are playing out in very localized ways.
Right.
And again, as long as you're consistent about how the rules are playing out in these localized ways, you can maintain a coherence.
Yeah, yeah.
So
So
you're right.
XOR is like
The
you look at
background
these
and the
two,
foregrounds.
if they're the same, use that color that they're the same on,
Hmm. Yep.
or do I have it backwards?
Or well, they could,
Wait,
yeah, there
no,
could be
exclusive or
setups.
right? It's if wait, no, if they're different, then which one do you use?
You decide. It's dictated locally. The answer is determined locally. So you just kind of look around relative to where you are. You say, what was can I find an example? You just
Hmm.
look, okay, the last time I did it, it's the opposite of whatever happened when they were the same.
I see.
It's difficult. It's very difficult to articulate. It's really easy to understand when you're doing it by hand.
Because
Maybe I should do
well,
a
if they're
movie, like one step at a time. But yeah,
that's an
you
interesting
can
coding
see,
challenge. Like I'm curious how I would
I,
start on a hex
yes,
grid and then start at the center and start like spiraling around and implementing rule this rule in this way.
I think, yeah, I think
But
there's
what
some
trips me up is
incredibly
like the fact
interesting,
that you kept changing colors at will or according to
but
some
maintaining consistency.
like what's the story on these purple dendrites that come down?
Yeah, so at a certain point, I was like, okay, so here you see that there's like a silvery and a silvery.
Mm-hmm.
You're in a little nook here, two, like three silvery ones. Like, I'm bored of putting only, what was I, dark green when there's, when it's same,
Mm-hmm.
when they're the same. I'm bored of doing the dark green when it's same. I'm gonna just put in a pink.
Uh-huh.
So I just stuck a pink in there and then moved on and kind of, I think there were then here. I put in a dark red.
Okay.
When it was
Yeah.
the same. So you can kind of so you can change the rules. You can add new colors into the rule space and say, and they become potential candidates for when the two cells are the same versus when they're different. Um, and then you just have to look locally to figure out whether you're now, this kind of created a pink world where pink became the option to draw on when the two relevant neighborhood cells were the same value. Um, and
Okay.
here
Okay. Yeah.
is the
Yeah. So
marine
it's
world.
you're always dealing in two colors. If these queries are the same, then put in the color that you're using for same, and if they're different, put in the color
Mhm.
that you're using for different. So those
Yeah.
those two colors that you're using, you can change those as you go around. All right.
Yeah. But you need to also introduce some rules for negotiating what happens when they encounter each other, for example. I have to
Mm-hmm.
confess, there's some stuff going on in this, even relatively early on, that are just like design choices of my own that aren't as sort of rigorous
Mm-hmm.
as as what I would have done if I were just purely making this as an illustration of how to gradually change these rules. But essentially, there are areas where you kind of have illustrations of gradual changes to the rules. So over here, for example, I sort of said, all right, let's see if I can, like, what happens if I throw in a few different colors when I have the option of adding some new colors and see how those colors kind of, if I get reminded to use those same colors in the next round, whether those colors then wind up kind of taking off. Um, so here you can see that there was like a little dark red one that I used
Mm-hmm.
on the round, but then the next round I went and I sort of stuck a dark green one, and then that kind of overtook that red one. So that red one never really had a chance to kind of grow and develop into a strand. It got overridden by a rule set that was associated with another color.
Yeah.
But like here, this pink one that I put in one row, I was like able to reference, I could see it because it's so brightly colored. When I came around the next row, I was like, oh yeah, I was in the pink world here. So I'll just throw in a pink one. And so so then the pinks really took off because I was able to notice the pink one because it really stood out compared to the others. So, aesthetically and in these beaded tapestries, it's kind of interesting. Okay, that's cute. But actually, if you think about it in nature, there are sort of signals that growing cells could be sending out. Some signals could be more um, easy they could transmit further than other signals. Like this dark red signal was not like strong enough in some sense for me to pick it up when I was in that next row relatively close by. But this bright pink one, the signal was relatively easy for me to pick up. So I was able to kind of like use that signal to continue to influence the design and growth of the object.
That's fascinating.
So
And
that stuff, there's a lot of teeny little lessons like that, which I think are
mm-hmm.
really interesting.
And that little uh dark cell that didn't phase out, it's also replicated on the same. Like the bilateral symmetry is ubiquitous.
Yeah.
Uh-huh.
Yeah. So
So when you
obviously
do you have to
that's by
remember that
design.
that you're like whatever I did on this side, I
Yeah.
gotta replicate on this side.
Yeah. But the reason it was relatively easy to remember as a human maker is because like it was this, I don't know if you can even see, but there's like actually a slightly different color green
Mm-hmm.
here than there is in that sort of background area. So this was kind of an open opportunity to potentially inject something new.
Mm-hmm.
It's because the two are because there wasn't anything before it telling me what color it had to be. And I was in a world where I now had a lot of options to use. So I just chose one of the options. And then nearby was I had already established what world I was in. I was in the slightly darker green world. So then when I got to the other side of that row,
Hmm.
um, no, it's actually not replicate. Yeah, it's not really replicated. I think I had just forgotten about that.
Uh-huh.
So in nature, you could think that that's like a mistake or something. Um, but that, because it was a relatively benign mistake and it wasn't replicated, it wound up not making a big impact on the resulting pattern. But this idea of how, like, you can start to introduce new components into a system, a rule-based system, and maintain the fundamental rule that dictates how these different elements interact,
Hmm.
but keep that on a local level. And then there has to be some kind of a sensing mechanism that that allows the growth to happen um, in some kind of orderly way. But it's very minimal. The sensing is very, very minimal. And the most important thing is just to be consistent. And then the symmetry kind of emerges. Now, obviously, the symmetry in the early stages is very easy to maintain and have a quick check visually.
Hmm.
As you get further and further along, it's harder to like know that you're not making symmetry is broken only by mistakes, really. Um, or by like putting in a new color. Um, so as it gets bigger, it's harder to check for symmetry, but
Hmm.
then the symmetry is less important as the thing gets larger. At least from an aesthetic perspective, and that may also be the case for many processes in nature. That symmetry is most important in the early stages of growth, and at the later stages of growth, you can tolerate a lot more complexity and asymmetry. And in fact, if anything, the asymmetries and complexity gives an opportunity for the form and the organism to experiment with new ways of managing itself in environments.
That's fascinating. Yeah, so the nucleus that you had whenever you started introducing those new colors at the center, if as so long as that was symmetric, then that created a symmetry for the entire thing.
Yeah.
That, and you have to stay consistent with your color choices from one area to the next.
Yep. Yeah. Yeah. This is the most complicated one that I've done so far.
Yeah. Can you show us some of your other beadwork? Maybe on
Um,
camera or um,
I
the screen.
mean, I don't, what I have to do then is go into, yeah, I don't have a very well organized thing. You have to go to my Instagram to do that. If you like, are you?
Um, let's see. Yeah, I can share screen and go to your
All
because
right. Do I
it's
have to
really
stop
great
sharing?
beadwork. Yeah, it really is fantastic. Um, all right, let's try it. Share.
Yeah.
Okay. Oh, that's cool.
Yeah, so I do these little forms. Those are here, this is a way to see. These guys, I make them, I bead these little creatures. They're like they're like aliens to me. Um, this I did. These were from about 2021. Um, and I scan them on a
Mhm.
flatbed scanner. And and this one I is a different one than this, but I sort of pulled it as I was scanning it. And I think it's very interesting to see um, how kind of you mess with time in some sense, because this is the way a scanner moves over an object. It's kind of like
Oh, I
how
see.
cellular automata plots are going in time.
Hmm.
And here I like dragged it while it was going in time. So
I see
yeah.
the kind of the rolling shutter sort of effect.
Yeah,
Um,
yeah, yeah, yeah.
okay, so here's another one that looks like a cellular automata based rule.
Yep, that one I'm still working on that.
Hmm.
That's Rule 90, just with a lot more colors.
Okay, yeah, I see the Serpensky coming in there.
Hmm. Yeah, there's like, oh yeah, that's one that is hanging on my wall.
Hmm.
That is yeah, it's very complicated. Also similar to the green one that I showed, but with these muted colors. When I sort of kind of referred to this earlier, when the colors are very similar to each other in a certain area, it means that I'm more likely to make a mistake because it's harder to differentiate
Hmm.
between to notice whether, you're between two beads that are the same or different colors. So, and that also makes me think about how errors in at least human errors are not like really random. There are certain conditions under which errors are more or less likely to happen. And so when I'm doing these bead weavings, it's much easier to make mistakes in areas where there's less differentiation between beads. Um, and, that makes me think that in nature, there are probably systems in which errors are more or less likely to occur because differentiation is harder to establish um, for certain qualities. So whether it's vibrations and it's harder to differentiate between the frequency of two different vibrations,
Hmm.
or if it's colors, or if it's, you know, smells, which arguably is also vibrations. Um, I think that to me suggests that error is a much more uh, it can be very targeted and it can signal certain information about the context. Um, here's another example. I don't know if this one
Ooh,
that's
I like that.
it's probably easier to see them in Instagram than if I hold them up, but
Well, I like
yeah.
that you're sharing it with the physical pieces with us.
A
So what?
stack of
Which one
them.
was that? Was that this one here?
It's one that looks like a Sacred Heart. No, this is looks like this with the white at the top and
I
then this
thought
bulgy
that
thing at the bottom.
is that not it then?
No, no, it's not that one, but that one's good too. They're all good.
This one's interesting. You went further along these wings than you did the other ones.
Yeah, that's
Oh,
this one here. Oh no, that's the one. Yeah. Yep. Yeah. This sometimes I'll start. I think this one I might have started. Yeah, this one. So this is interesting because I started with a triangle in the middle, like the
mm-hmm.
ones that I've been talking to. And then I built out on the sides, two sort of wings going out. Um, yeah. And I think, yeah, using Rule 90 for those two. Yeah.
I can see a stitching pattern here where like it went from expanding outwards to continuing along a particular
Yeah.
width.
Yeah. Yeah. I mean, sometimes you know, I'm not, mostly I'm following exactly like a Rule 90 or whatever rule I've chosen to use, but sometimes I'll just do something a bit different in the um yeah, the first one I did in these flat patterns is the one, it's sort of at the low end on the left of, it's like a pinkish one with those dark inclusions. That was the first one
This one,
that I did. Mm, no, it's a triangle. It's like it's up now. It's on the top row relative to what we're seeing on the left.
this one,
Not, it's the one next to that one, but yeah.
this one.
No. Anyway,
uh,
yeah, there are a lot.
there are.
Um, and I'm continuing to do this work. I'm very interested in developing some kind of a software solution that lets me kind of go and change in the way that I'm actually doing it, beat it, introducing new colors into areas and then capturing computationally what the rules are
Uh-huh.
that maintains the consistency, the local consistency. Largely, those are like hierarchies among colors. So, if a dark green bead encounters a pink bead, it, the dark green bead becomes the background color or something like that. But I haven't yet had the discipline to sit down and articulate this computationally, but I know that there's a computational approach that we could use to build a tool to allow a sort of creative space to design these in an interactive way where you're changing the rules and then it propagates for the rest of the piece. And even potentially introducing the ability to create error or simulate error,
Hmm.
which I think would also be interesting. That one I gave to Steven, the dark,
Oh
the
yeah.
gray and black one. Yeah.
This one here, or the
The gray and black one that you had just no, not that one.
whoops,
The one that has 54 hearts,
54 hearts, huh?
which sits on top. Yeah, it's the same one as the one just below it with the orange background. I don't know why I just have two different pictures. I sort of took a goodbye picture before I gave it to
Hmm.
him. Yeah. The blue one with the yellow looks sort of like a video game.
This one here.
No, this one's kind of, it's the one below my work in progress profile picture. Um, the one that's in the shape show. Yeah. This one has a video game kind of quality to it. Why did it not open?
I just went back to your page. The link to your
No.
page is not a link to the picture that is holding you're holding one
Hmm.
up.
Yeah. But I mean, I like to, I do mostly beadwork, but I do like to kind of explore with other materials too. One thing that I should probably mention is I just completed a project with Phileas.
Hmm.
doing this uh, this art organism where a bunch of us got to sort of over the course of several weeks, we created new works that were inspired by works that other people had done in the previous weeks. And Phileas created this network uh, illustration that you can navigate and explore to see how all the different artworks evolved over time and how they related to other artworks that were done by other artists earlier in the various cycles. And I think Phileas is going to present this in a few different contexts. So you can look forward to learning more about that. But some of the pieces that I have here were things that I did when I participated in Phileas's project.
Yeah, I remember him
Another thing I like.
talking about that project. It's really interesting. Um, maybe we'll have him on for a live stream to show us.
I recommend it. I
Yeah.
recommend it. Yeah, it's really worthwhile. Another thing that's kind of fun is using some of the image generators, AI image generators to play with these objects. AI really back to the art for robots thing that
Hmm.
I was inspired by how AI really responds to these pieces. Seems to like it's I don't know if it's regarding them as I'll just say it like this, regarding them as something special, but there's one in particular, there it looks like so so you see that shape show thing, sort of catty corner from that below is yeah, there's like a little guy, there's like a it's not a triangle, it's actually more of a um I don't know how to say it. There are these it has a little video um mm, top. Okay, yeah. All right. So the top row, far left.
This
Yeah,
one.
click on that one.
Okay.
Yeah. And then you probably have to go forward. Sorry for the honking. I'm going to put this.
Oh, cool.
Yeah, now scroll to the right a few. Yeah, yeah. To go to the right. I think there's a video. You play the video. Oh, yeah. This is I guess it's not showing up as a video when you show it this way. But anyway, it's a Sora created video that spins it around and makes it look like protein folding.
Oh, that's
Which
fun.
is very,
So you gave it like an
yeah,
image and told it to guess at the rest of it.
yeah, yeah,
Mm.
yeah,
And it's doing its best, but it like makes it look like a weird kind of
yeah,
a lot
yeah.
of
But it
texture.
reminds me, yeah, so in a recent conversation that Stephen Wolfram was having, I think it was on Theories of Everything, where
Hmm.
he was talking about how he fed some of the cellular automata pictures into an LLM and asked it to describe it in the style of an old biology textbook.
Hmm.
And, you know, the way that the language that it used and the way that it was describing these images was very evocative to him. And it sort of suggested that, you know, these were kind of the types of patterns you see in nature, right? Confirmed that to him. And I think that that's a similar phenomenon to when I add these images to LLMs. The way that they process the images is really like taking the nature references and working with the nature references quite, yeah, or the protein folding or the very scientific objects.
Hmm.
You know, it seems to regard them as very scientific objects, which it's satisfying. Yeah.
Um,
Well,
we have a comment on YouTube uh, from halfway through the presentation. Nectar Intellicane. I don't know how to pronounce that username, but they're saying about XOR. They're saying it's very relational. It's a great metaphor for memory and value in general. Makes indigenous beadwork stand out as an elegant technical device for transmitting ancestral values as well as rulio.
yes, I completely agree. It's pretty mind-blowing.
Yeah.
I think that we need to go back and reinvestigate these ancient traditions, these older traditions with a computational lens, I think we can learn quite a lot by taking this computate, there was a lot of information in those patterns that I think has gone underappreciated.
Yeah, and then they go on to say if optogenetics work with light, could it work with bead patterns similarly?
Not sure what optogenetics is,
Um, Optics and genetics. I'm not sure either. But
but I'm like gonna say yes. 'Cause that's how I think.
um, so Brian Silverman put the first bead pattern into GPT and asked it to generate something. Says this is the output. It looks like a zoomed in pixel or bead based rendering of a cellular automata or fractal pattern, possibly something generated by a Wolfram 2D rule or repeated triangular tiling of a 1D automaton like Rule 90, mirrored across axes.
Good. Yeah.
Yeah, that's pretty much spot on.
Yeah.
You can go on GPT.
Yeah. I did it. I've done it a few times and I was gonna read one of them, but it was getting a little bit long, but I
Mm-hmm.
appreciate Brian instead of me.
Well, um, thank you so much for presenting your beautiful artwork and
Thank you.
your really logical findings. Um,
Thanks.
Thanks for everyone tuning in on the live stream.